Let's go over Activity 12. So for question number 1, we'll be looking at the ex9.store data frame. And this is a data frame that was created by a bank that was keeping track of whether or not particular customers were shopping or not shopping at a collection of stores. And these stores have all been anonymized, so they're just referred to as store 1, store 2, etc. So let me load in reg class and then load in the data frame. And the purpose of this question is to develop a model that helps to predict whether a customer buys at store 8 based on the shopping habits from other stores. So since we're trying to build a predictive model, it's important to make a holdout sample so that we get a genuine assessment of how well our model actually predicts on new data. So we're going to pick rows from our original data at random to fill in the training set and the holdout sample, and then we'll do all our model building process on the training sample. Alright, so we're going to reserve 60% of the rows to be in the training data. The remaining 40% will be in the holdout, and these 4 lines here will accomplish that feat for us. Alright, part B asks us to build a partition model using the build.tree command. So to use build.tree, what we do is put in a formula very similar to what we would do for regression. We want to put in the name of our y variable here. We're trying to predict store 8. And in this case, we're going to use all of the other predictors as potential predictors in our model, so we can do twiddle dots. And the key thing here is that we're going to be using data equals train because we want to be building these trees on the training data. After we've made our final decision, we'll make predictions on the holdout sample. We don't want to use the original data because we've split it into 2 here. And one other thing is that we want to make sure to add in the argument seed equals 320 because the estimated generalization error of the trees are being found with repeated k-fold cross-validation, a random procedure. If we want to reproduce the results, we need to make sure to set the random number seed. If we don't do this, it's very possible to get a different tree each time we run the command. All right, so we can run this, and then we can look at the results. So on the right here is a plot of the relative estimated generalization error of the different trees as it was being built, as new rules were being added, versus the number of splits. So we start out at 1, basically no model at all, every individual in the same partition, and we see that adding a few rules helps out the tree. It looks like the estimated generalization error decreases to a point, and then actually the tree starts to become overfit. Adding more rules actually makes the estimated generalization error of the tree get larger and larger. The tree is becoming overfit there. Alright, so what's the value of CP and the number of splits in the partition model with the lowest estimated generalization error? Well, looking back at this output here, we see that the lowest estimated generalization error came from a tree with 12 splits, and the value of CP was this number here. So I'm just going to copy and paste this value. This value is a rough measure of how much the tree needs to improve in order to justify adding in a new rule. So smaller values of the CP indicate trees with more rules because it doesn't have to be as much an improvement to justify adding in a new rule as it would be if we had a larger value of CP. All right, what's the value of CP and the number of splits in the partition model selected by the 1 standard deviation rule? Well, it's highlighted for us here, so we can just copy and paste these values. So the 1 standard deviation rule says that's nice that you found the tree with the lowest estimated generalization error, but we could probably get away with a simpler model. Any model whose estimated generalization error is within 1 standard deviation of the absolute lowest value is roughly equivalent from a predictive standpoint. And so since these red bars give plus and minus 1 standard deviation from the estimated generalization error, any model that is, has an estimated error that's below this horizontal black line is suitable for our purposes. So we go with the simplest model we can, and that's the one highlighted right here. All right, does the partition model show signs of being overfit as the number of rules added to it gets increasingly bigger? Yes, it does. The estimated generalization error starts to get significantly larger beyond about 12 splits. That's what we see, the estimated generalization error getting bigger and bigger and bigger, indicating that the tree is essentially memorizing the training data, the quirks and characteristics that are unique to it, which it isn't finding in the data as a whole, and so we actually make worse predictions. All right, part C asks us to fit our final tree here, the tree selected by the one standard deviation rule. So I'm going to call our result tree. Our command is rpart, and our formula is just like what we've been working with. Our y variable, twiddle, then whatever the list of variables we want to be predicting from. So store 8 twiddle dot in this case, making sure that we're building this on the training data. And the only thing we have to do is put in the CP parameter that we want the tree built out to. So we say CP equals the one suggested by the one standard deviation rule. All right, then we're asked to also look at the results of summarized tree. So let us look to see how important each variable is, and then visualize tree. We can actually see the decision tree associated with the partition model. All right, so let's fit the tree. And part C1 asks us to consider variable importances. So we can do summarize tree to get an idea of which variables were and weren't important to this tree. And the numbers themselves don't mean anything specific. It's only when we compare the numbers to each other do they really obtain any sort of meaning. The larger the value, the more important in a sense that predictor is. So which 3 of the 67 other stores appear to be good predictors of store 8, whether or not the person shopped at store 8? Well, these top 3 right here. So we can just copy and paste that. C2 asks to imagine a shopper that buys at all even number stores but doesn't buy at any odd number stores. So we'll use the tree to predict the probability that this shopper buys at store 8. All right, well, to do that, we need to actually visualize that tree. And let's actually do this right. Visualize.model. All right, so how do we make a prediction? Well, we start up at the top, and then we use the rules as we need them. So the first question that we need to ask is, does this person buy at store 13? Based on the answer, we'll head off to the left if the answer is yes, and we'll head off to the right if the answer is no. All right, so we're told that this shopper shops at even number stores, but not odd number stores. So the answer to this question is no. That brings us down here. We need to ask ourselves, all right, does this customer shop at store 17? Well, the answer to this is no, so we once again head off to the right. Does the shopper shop at store 22? Yep, so we head off to the left. Does the shopper buy something at store 36? Yes. So here we end up in our final partition. It looks like there are 112 similar customers in the data frame. And of those customers, about 2/3 end up buying at store 8. So we would predict this customer to buy at store 8 with a probability of about 62.5%. All right, so 62.5% is our answer. Part C3 follows up on this. How many other shoppers in this data set are in that final partition? Well, that's the 112. That's the number that's labeled right beneath the partition there. All right, so how well does this tree actually do at predicting genuinely new customers? Let's find the generalization error on the holdout sample. So we can run the command generalization error, passing to it the model we want to be checking, and then the name of our holdout sample. And let's see. All right, so report the generalization error of this model on the holdout sample and compare this to the misclassification rate of the naive model. And then finally, see whether or not this model generalizes well. All right, so we're given 2 chunks of information, the performance on the training data, which we don't care about right now, and the performance on the holdout sample. This is where we want to know the misclassification rate. So it looks like we have a 44% misclassification rate on the holdout sample. That's not all that great. 44% misclassification rate. What would the naive model predict for the holdout sample? Well, in the holdout sample, it looks like the naive model would be predicting everyone to be a buyer, because it looks like in the training data, which is the only data that all the models have access to, the naive model says, okay, whatever the majority does, we'll predict for everyone. And in this case, it looks like the majority buys. So the naive model is going to predict everyone to buy in the holdout sample. So it's going to make errors on 265 of the individuals in the holdout sample. So we can divide 265 by the 600 people in the holdout sample for a misclassification rate of 44.2%. So our partition model just barely beats out the naive model. It's really hardly better than it at all. So the naive model would predict everyone to buy. It's the majority level in the training data. So it makes 265 out of 600 errors, or a misclassification rate of 44.2%. Just our model's just barely better here. So do we say that this model generalizes well to new data? Well, that's where we actually compare the misclassification rates on the training data to the misclassification rate on the holdout sample. And if our model is generalizing well, then these two errors should be roughly comparable. And the general guideline is that we want to check to see if the error on the holdout sample is no more than about 25% larger than the error on the training sample. So how much larger is the rate on the holdout sample? Well, the difference between these two is 11, or 0.11. Dividing that by the misclassification rate on the training sample, we see that's an increase of about 33%. So no, this model, not only is it just barely beating the naive model, but it's really not generalizing well. It's fitting the training data a lot better than it is fitting and predicting the data in the holdout sample. So this model does not generalize well. The misclassification rate on the holdout sample is about 33% higher than the rate on the training sample, 44% versus 33%. All right, so not that successful of a model. So a random forest takes a slightly different approach. It actually creates 1,000 different partition models, each of which are constructed slightly differently, and then combines the prediction. So does a random forest model do any better at predicting whether or not a shopper shops at store 8? Well, let's fit it. Since the random forest, like the name suggests, is a random procedure, we always want to make sure to set the random number seed right before we run the command so that we can reproduce the forest if we need to. Otherwise, we could get a different forest out every time. So store 8 twiddle dot, fitting this on the training data, and then using 1,000 trees. So the individual partition model was a pretty weak predictor of whether or not this shopper actually makes a purchase at store 8. But maybe there's strength in numbers. Maybe the random forest model will make better predictions. Let's see. So how well does the random forest model generalize to the holdout sample? Well, that's a little disappointing. The misclassification rate is definitely lower, but it's not a lot lower than the naive model or just that single partition model. So the misclassification rate is 40.8%, which is only slightly better than the naive model or single partition model. All right, so very often random forests do better than regression models, single partition models, etc. And in this case that's true, but it's just barely doing any better. This looks like it's just one of those really difficult problems to actually be making predictions for, and most likely there really isn't going to be any technique that's really going to ace this problem. Most of the model building techniques aren't going to succeed in really that successfully predicting whether or not the shopper makes the purchase at store 8, it looks like. All right, let's just see, if we were to do a regression for this, and regression is rarely the place that we want to be when we're doing predictive analytics, how well would a logistic regression model do? Well, in this case, let's actually do a search for it because logistic regression model building is so slow that we just don't have time for that. And so to do a search, we're going to fit the naive model and then the full model, no interactions here. So the naive model can be fit with just y twiddle 1. The full model can be fit with y twiddle dot if we're not going to consider any interactions. And since we're doing logistic regression, we got to make sure to have that family equals binomial and that we're using GLM instead of LM. So we'll fit both of these regression models. And then we can run the search. Let's start out with the naive model, restrict our search to any model within the naive to full model range, and let's try direction equals both. So at each step in the process, we consider adding in a new variable that's not in the model and kicking out a variable that is in the model and see what move would drive the model closer to the truth, basically decrease the AIC the most. And I'm going to have trace equals to 0 because I'm not really interested in looking at the model building procedure as it progresses. So we'll run this, and logistic regression model building is very slow, so this will take a while. But I can set the next command up. We're going to get the generalization error of this logistic regression model on the holdout sample. How well does it do? Okay, well, the misclassification rate is 43%, which, if we look back, what was the misclassification rate of the single partition model? 44%. So in this case, beat the partition model by just a little bit. What's the misclassification rate of the naive model? 44.2%, so just slightly better. But it doesn't do as good as the random forest model. And that's typically what we see. So the generalization, or the misclassification rate on the holdout sample is 43%. Better than the naive model and single partition model, but not as good as the random forest. And that's typically what we end up seeing. With predictive analytics, the random forest is better than the regression model, which in turn is typically a little bit better than the single partition model. All right, so when y is the categorical variable, typically the random forest will be the go-to predictive model. Does it happen to do the best on the holdout sample? Here, yes, it does. All right, question number 2 wants us to look at the CUS loyalty data set. And in this, we're trying to predict the customer lifetime value based on a bunch of that customer's characteristics. If they're a male or a female, if they're married or single, how many total transactions they've made at the store, the value of their last transaction, etc. So once again, what we need to do is we need to split the data into the training data and then the holdout sample, so that after we're done building that model, we can get an honest assessment of how well it makes predictions on new data. So we'll be splitting 60% of the data into our training data. The remaining 40% will be our holdout sample. All right, so we'll start out with the partition model, so we can use build tree. And in this case, we're trying to predict customer LV here, twiddle dots using all variables, making sure that we fit this on the training data, and passing the random number seed for reproducibility. So there we go. What's the value of the CP and the number of splits in the partition model with the lowest estimated generalization error? Well, it looks like the very lowest generalization error was found with the CP of 0. Basically, any rule added to the tree will do. We can build it to the maximum possible size. So CP equals 0 with 30 splits. So the only restriction on building a partition model is that there needs to be at least 5 individuals in any particular leaf. So in this case, it looks like the maximum possible size tree here has the lowest estimated generalization error, kind of making the tree the biggest it can. All right, well, the one standard deviation rule says that we could probably get away with a simpler tree without too much loss in accuracy. So what is the value of the CP and the number of splits with the one standard deviation rule? Well, we can just copy and paste these values here. We may be able to get away with a tree with just 7 splits without losing too much accuracy. All right, so does the partition model show signs of being overfit as the number of rules added to it gets increasingly bigger? Well, in the last problem, we saw signs of overfitting, but in this case, we don't. We actually see that the generalization error, as estimated with the repeated k-fold cross-validation, just continues to get better as we increase the number of splits. After a point, it doesn't really decrease by much whatsoever, so making the tree more complex isn't really improving it all that much. But we don't see any sort of uptick in the generalization error. We don't see the tree getting worse and worse at predicting new data as we make it more complex. So no, the generalization error does not increase as the number of splits increases. So it doesn't look like that. In this case, the tree is really overfitting the data here. All right, so since we prefer simplicity if we can get away with it, let's go ahead and fit the model suggested by the one standard deviation rule. So we'll use our parts, and we're going to predict customer LV from everything on the training data using that CP suggested by the one standard deviation rule. All right, so we're going to summarize that tree and visualize it. And we'll talk about some of the results. So we'll start out with summarizing the tree, which is the most important predictor of the customer's lifetime value. Well, looking at the variable importances, the numbers themselves don't mean anything specifically, but comparing the numbers kind of helps us pick out which is the most important. And it looks like tote transactions is the one at the top of the list here, with a larger value than the wallet share. The 8 predictor variables, which is the least important, and heads up, this is sort of a trick question. What you'll notice is that if we scan through this list of important variables, one of the variables in the original data is missing. So married actually is the least important because it's not even on the list. For all intents and purposes, its importance is 0. All right, so we can use this tree to make predictions. Let's visualize this model and get a little bit of practice here. Here's our tree. And let's make a prediction for the customer lifetime value of a male customer who's married with an income of $63,000 and who does not have a loyalty card. Assuming that that customer's first purchase was $100, this customer's wallet share is $100, and that this customer's made 15 total transactions. All right, so a lot of information. What do? We start up at the top and then answer the rules as we're presented to them. So what is the customer's total transactions? Is the answer to this question, is their total transactions less than 7.5, yes or no? Well, in this case, we have 15 total transactions, so the answer to this question is no, and that brings us to the right. We're asked to reconsider total transactions. Is it less than 10? No, it was 15, so we head off to the right again. Is this customer's wallet share less than 87? No, it was 100, so we head off to the right once again. Was the customer's value of first purchase less than 139? Well, their first purchase was 100 here, so the answer to this question is yes. So we head off to the left now, and we find that we make a prediction for their lifetime value of 2322. How many other customers in this data set are in the final partition? How many other similar customers that look like we have? Well, it looks like there are 26 other customers that have the same overall characteristics, so we would say this is the average of 26 other customers' lifetime values. So what's kind of interesting is that we had all this extra information, the gender, marital status, the income, loyalty card status, but we didn't use a lot of that information when making our decision. And in fact, we see that some of these variables don't even factor in to the rules presented by the partition model at all. So sometimes not all the information we have is really all that relevant to making our prediction. All right, so how well does this partition model make predictions on brand new data? Let's see what the generalization error is on the holdout sample. And it looks like that we are predicting customer lifetime values on the holdout sample to within about $258. The typical error on the holdout sample is $258. So the typical error on the holdout sample is $258. Does the model generalize well? Well, we compare the training error to the holdout error here. And we expect the error on the holdout sample to be a little bit bigger than the error on the training sample. It's harder for the model to make predictions on data it doesn't know about than data that it does know about. It just can't be too much bigger. So what's the percentage increase? Well, the increase is 258 minus 243. Divided by the error on the training sample, it looks like an increase of 6%. That's hardly anything at all. That's fine. That's less than 25%, so we're happy. So the increase in error from training to holdout is 258 minus 243 over 243, about 6.2%. This is less than 25%, so we can say the model generalizes well. All right, well, a single partition model tends to be a relatively weak predictor, but there's strength in numbers, so let's fit a random forest model to see if we do any better. We usually do, not always. So let's set the seed to 320, and let's fit the forest. So random forest predicting customer LV from everything on the training data using, in this case, 1,000 trees again. So we set the seed, run it, and then we're going to look at the generalization error of the random forest and see, do we do any better? All right, single tree had a typical error of about $258. Random forest blows this model out of the water with a typical error on the holdout sample of only $174. So the typical error on the holdout sample is only $174 here, much below the generalization error of the partition model. That's what we usually see. A single tree, a pretty weak predictor of our y variable, but strength in numbers, the random forest, combining the results of many, many different trees makes a much better prediction here. All right, well, we can see how regression does. We don't really want to be in a place where we're using regression for predictive analytics, so let's just see if we do as bad as I keep saying we're going to do. So let's use build model with no interactions here. And it'll take a while because regression is relatively slow compared to partition modeling. And we want to fit the model using the predictor suggested by the one standard deviation rule to keep things simple. So let's LM this. The model with the one standard deviation rule has this formula right here, which we can copy and paste. There aren't any categorical variables, so we can use that formula directly. We're fitting that on the training data here. So there's our regression model. How well does the regression model predict on that holdout sample? 188. So the typical error of the regression model on the holdout sample is $188 here. All right, so which method happens to perform the best on the holdout sample? Well, what we saw was that the random forest model had the error of 174 versus 188 from the regression versus something a lot bigger for the single partition model. So same sort of story as what we had last time. The random forest model performs the best on the holdout sample, followed by the regression, followed by the single partition model. And that's usually what ends up happening. So random forests, great for predictive analytics, typically do a lot better than regression models, but they serve as kind of a black box. You put stuff in, you get something out, but you have no understanding of how the model is really treating the relationships between your y and your predictor variables. So visualize.relationship is an attempt to try to rectify that, to try to actually show you how the random forest is modeling the relationship between the y and the x variables. And in fact, you can use this command to see how any sort of model is actually modeling the relationship between y and a particular predictor. So what we do with visualize.relationship is to give the name of the model we're interested in studying, put in the variable of interest, basically our x variable that we're interested in isolating, what data set the model was built on, and then we can say marginal equals false so that we see the various aspects of the relationship. Basically, it singles out characteristics of 5 individuals in the data and shows us what the relationship looks like between y and our x variable for that particular set of characteristics. So the regression model, with no interactions, gives the same story regardless of the other characteristics of the customers. With no interactions, the nature of the relationship between our y variable and our x variable is assumed to have the same structure. We might have different intercepts, but it's always the same slope here. So the regression model is assuming just a linear relationship between the predicted customer lifetime value and total transactions. Sometimes it might be a little bit higher versus lower based on the other characteristics, but the form of the relationship is always going to be a straight line. Well, how does the partition model view this relationship? Well, here's how the relationship is being modeled for 5 different customers, predicted customer lifetime value versus total transactions. And we see that the partition model is able to naturally incorporate nonlinearity in the relationship. Now, the exact nature of that relationship depends on what particular set of characteristics we're focusing in on. And so we see that the partition model kind of is able to pick up on more general types of relationships, a little bit of nonlinearity in there. What about the random forest? How's the random forest modeling this relationship? Well, for 5 particular sets of characteristics, here is how it's modeling the relationship between lifetime value and total transactions. And we see that sometimes, it's treating that relationship as roughly linear, like the red line right here. Other times, it's treating it as roughly nonlinear here. This yellow line has a little bit of a curvature. So just kind of interesting to see how the different models are approaching the relationship.